Just like we did before with the single and then moving into the repetitive, we're going to look at the repetitive pulse response now to DC differentiators, just like we did for the integrator. So the RC integrator response to a single pulse that we just covered now is extended to repetitive pulses, and you'll see that essentially the logic is the same. If a periodic pulse waveform is applied to an RC differentiator circuit, two conditions then again are possible. The pulse width will be greater than or equal to 5 time constants, or the pulse width will be less than 5 time constants. So if we look at the figure, it shows the output when the pulse width is 5 time constants. As the time constant is reduced, both the positive and negative portions of the output become narrower. Notice that the average value of the output is 0. An average value of 0 means that the waveform has equal positive and negative portions. Okay, and that this makes sense with what we've seen before with sinusoids. Okay, if they're equal, positive and negative, the average is 0. The average value of a waveform is its DC component, not its AC component. Because a capacitor blocks DC, the DC component of the input is prevented from passing through to the output, resulting in an average value of 0. So we can see here from the two waveforms, the one below shows that the steady state output when the pulse width is less than 5 time constants. As the time constant is increased, the positively and negatively sloping portions become flatter. For a very long time constant, the output approaches the shape of the input, but with an average value of 0. Okay, so thing to remember here with your pulse width equal to 5 or your pulse width less than 5 time constants. The RC differentiator response then to a single pulse is extended then when we look at the repetitive pulses. Okay, so we can see how the waveforms change here with repetitive pulses as we move through the RC differentiators. Like the integrator, the differentiator output takes 5 time constants to reach its steady state. So there's your input, 1, 2, 3, 4, 5 time constants to get to the output. We do not care what the circuit time constant is at this point because we know that the resistor voltage will decrease to approximately 37% of its maximum value during one pulse or one time constant. So the differentiator output waveform during the transient time for the circuit looks like this. So you can see what's happening here. First pulse we get the maximum value 10 volts, then it decreases and it decreases, and here it's decreasing. Okay, so we end up having our values then shifted here. We go from minus 6.32 to minus 7.18 and minus 7.29. So again, let's take a look at an analysis of the repetitive waveform just like we did before. Like the integrator, the differentiator output takes 5 time constants to reach its steady state. To illustrate the response, let's take an example in which the time constant equals the input pulse width. At this point, we don't care what the circuit time constant is because we know that the resistor voltage will decrease to approximately 37% of its maximum during one pulse or time 1 tau. Let's assume the capacitor then begins initially uncharged and then examine the output voltage on a pulse by pulse basis. The results of the analysis then will follow the circuit shown in 2031. So for the first pulse on the rising edge, the output instantaneously jumps to plus 10. then the capacitor partially discharges to 63.2% of 10 volts, which is 6.32. Thus, the output voltage must decrease to 3.68 volts as shown in the figure. On the falling edge, the output simultaneously makes a negative going 10 volt transition to minus 6.32 volts. Minus 10 volts plus 3.68 volts gives us that minus 632. Okay, so we can see that here. There's our first pulse. We can see the changes that occur percentage wise. Between the first and the second pulses, the capacitor discharges to 36.8% of 6.32 volts now, which is 2.33. Thus, the resistor voltage, which starts at minus 6.32 volts, must increase to minus 2.33 volts. Why is this? Well, because the instant prior to the next pulse, the output voltage goes to zero. Therefore, the sum of the voltage on the capacitor and the voltage on the resistor must be equal. So the value of 2.33 volts minus 2.33 volts gives us the zero mathematically. Remember that V sub C and V sub R must equal Vn at all times in accordance with Kirchhoff's voltage law. On the second pulse then, on the rising edge, the output makes an instantaneous positive going 10 volt transition from minus 2.33 volts to 6.67 volts. Okay, so we can see that here, minus 2.33 volts jumps to 7.67 volts. Okay, that is the second pulse on the rising edge. Then, by the end of the pulse, the capacitor discharges 0.632 times 10 volts minus 2.33 gives us 8.45 volts. Thus, the capacitor voltage increases from 2.33 volts to 2.33 volts plus 4.85, which gives us 7.18. Okay, so there we are making that transition. Okay. So on the falling edge, the output instantaneously makes a negative going transition from 2.82 to minus 7.18, again as shown in the diagram. Now between the second and third pulses, the capacitor discharges to 36.8% of 6.18 volts, which is 2.64 volts. Thus, the output voltage starts at minus 7.18 and increases to minus 2.64 volts because the capacitor voltage and the resistor voltage, again, must add to zero at the instant prior to the third pulse. The output is zero. Okay, so we're here. On the third pulse, then, the rising edge, the output makes an instantaneous 10 volt transition from minus 2.64 volts to plus 7.36 volts. Then the capacitor charges 0.632 times the difference in 10 volts and 2.64 volts, which gives us 4.65 volts to 2.64 volts plus 4.65 volts, or 7.29. As a result, the output voltage drops to 368 times 7.36, which gives us 2.71. Okay, so we're here now at the third pulse. After the third pulse, 5 time constants will have elapsed and the output voltage is close to its steady state. Thus, it will continue to vary from a positive maximum of about 7.3 volts to a negative maximum of about minus 7.3 volts with an average of 0. So after that, as we continue down 4 and 5, we are definitely in the steady state portion. Okay, so again, take a look at this diagram, read through this so that you understand it. so that you understand what's going on with each of the pulses as we move repetitively into the steady state condition. So when we come back, now we move into the RL realm and into integrators with pulse inputs.